Hello and welcome to today's physics lecture wherein we shall be discussing the concepts as current and magnetism. Right? Now, as in the previous classes or standards we have discussed about that like earth, it behaves like a magnet. A bar magnet, a huge bar magnet is inside the core. Right? And also we have understood that what B is. First of all, let us recapitulate the things. B is known as the magnetic field. And when a magnet is over there, a north pole and a south pole, the magnetic lines of force due to this B, they come out from the north pole and enters the south pole, which is outside the case of this bar magnet. But when it is the case of inside this bar magnet, this thing will mean that the south pole and the north pole, the direction of the flow of the magnetic lines of force will be from the south pole to the north pole, right? Say for example this pen. When we write externally, the ink flows from the north pole. But if you look at the interior design of this pen, the ink actually flows from the south pole to the north pole. So likewise, the magnetic field, it flows in like this pen. Like there were various experiments that was conducted while we were undergoing this magnetism, right? But have you ever thought that why this concept is known as current and magnetism? Why not simply magnetism? We know that the current is due to the electric field, right? And magnetism is due to this magnetic field. So, like, what is the correlation between them? Oersted, during his lecture demonstration, once found accidentally that due to a current carrying conductor, there was a current carrying conductor like this. The current was flowing through it I. And the magnetic compass, when it's placed like far away from this, it was giving the direction somewhat like this. But when this compass is brought nearer, the same compass is brought nearer to this current carrying conductor, he was amazed to see that the direction of the mariner's compass changed. This was observed accidentally while he was demonstrating a lecture at the university. After that, 4 French physicists actually worked on these concepts. The first 22 was Francois Arago. The second one, famous André-Marie Ampère. Third one is the Jean-Baptiste Biot. And fourth one to do is the Félix-Savart, right? So, right now we are going to study about the law which is given by Jean-Baptiste Biot and Félix-Savart in collaboration. Is known as Biot-Savart Law. If we are going to understand this like Biot-Savart Law, definitely we will understand that why this thing is going to happen, and then only we can understand that why current and magnetism is the name of the topic and what are the effects of current on a magnetic field, right? So Biot-Savart Law states that let us take a wire. Say for example, we have taken a long wire like this, right? Say for example, here is the battery right? So the current will flow like this because this one is a positive and this one is a negative. The current will flow likewise. Now let us say, for example, take a very small region. Say for example, let us take a very small region. If the total length of this conductor is L, then we can denote this small length as dl, right? And if we do take this conductor, this small piece of current carrying conductor where current is flowing through it likewise in this direction, we can say that if we forget about the other parts, this dl will actually look like this, right? And this mariner's compass is at a point somewhere nearer to this. So we can place a mariner's compass over here. Say for example, at this particular point the mariner's compass is at this point. Then we can say that the distance from this to this, let this be small r, from dl to the point where this mariner's compass is being kept. So we are going to find out the magnetic field at this particular point, which is kept at a distance r from this dl, right? Now the Biot-Savart Law, it states that the magnetic field which is produced, the magnitude of this magnetic field, because as you see that this is a vector, obviously it will get a magnitude as well a direction. So let us first of all be worried about the magnitude. It states first of all that the magnitude of this is directly proportional to the current that is flowing through dl, which means that the current is flowing through dl in this direction, and this will be I. So the magnitude of this magnetic field which is being produced will directly be proportional to the amount of current that is flowing, which means that the amount of charge that is being flowing per unit time, right? Now after that it states that this magnitude of magnetic field is inversely proportional to the square of the distance of separation between the points, that is r. So it will be stated as 1 by r square, or is inversely proportional to r square, right? Now third point is, what is stated in the Biot-Savart Law is that this magnitude of the magnetic field will again be directly proportional to the length of the conductor being taken. Here the length of the conductor is a small part, a small piece of this entire one, right? We are only worried about the magnetic field at this point, say A, only due to this small part dl. So this be at point A, the magnitude will be directly proportional to the length of the conductor, or dl, right? Now the fourth point which is stated is as the angle between, see this dl, if it is like kept like this, okay, and this is the r, there must be a certain angle of difference between them. So let us say that this angle is equals to theta, right? It states that the magnitude of this magnetic field is directly proportional to the sine of the angle between this R and dl. If we are going, this is all about the Biot-Savart Law. Now let us look about the expression that could be deduced of this Biot-Savart Law. Now if we are going to take all of this at one go, we shall find that the B is directly proportional to I dl sine theta divided by r square. I GL sine theta, all are directly proportional, and it is inversely proportional only to the r square. So we can write it likewise. To change this proportionality into equality, we have to take the help of a constant. So B will be equals to K multiplied by IGL sine theta divided by r square. Right? Now, it has been experimentally observed, and then the value of K is determined as mu naught divided by 4 pi multiplied by IGL sine theta divided by r square, where we could say now that this K is equals to mu naught divided by 4 pi. So this K is equals to mu naught divided by 4 pi, where the mu naught is known as the permeability of free space. Right? Now what is permeability? Like, say for example, this is the permeability of free space. Let us say for example that this is a substance, right? And within this substance, this B or the magnetic field is going to get through. Or in simpler words, to understand this concept in a very simple go, this B has to penetrate it. So how much this substance is going to get, like to allow the B to penetrate it. It is simply like this, right? Now say for example, if this is not in a free space or inside some like a different material, where we could say that if the relative permeability, where mu r is the relative permeability of a medium, right, then we could say that mu is equals to mu naught multiplied by mu r, right? So had this been the case where this thing is happening in say water and not in free space or air, then the value of mu naught would have been replaced by mu, where mu would be equals to the permeability of free space multiplied by the relative permeability of say water in this scenario, right? But in this entire scenario right now, we are going to take, say for example, that the medium we are taking is free space or air, right? So in any case, in any of the sections throughout the entire topic of current and magnetism, if you to find out that water is given or some any other medium is given, it is recommended to change this mu naught into mu, where the value of mu will be equals to mu naught multiplied by mu r, right? So this is the expression which is being given by the Biot-Savart Law. Now, we were discussing about the magnitude. And what about the direction? So for example, like over here, we need to find out the direction, that in which direction the magnetic field will act on A, or in which direction, say for example, of the same arc. This is arc over here, and we are taking another point of the same distance, but on the other side, say for this point is B. So what would be the direction B now? Since over here, like this is R, say for example, we are going to see this A, the magnitude of this magnetic field at point A will be equals to this one. Now, for determining the direction, we have to take the help of the Cork-Screw Rule or Maxwell's right-hand thumb rule. Right? Now, what does the right-hand thumb rule indicates? Say, for example, this is DL, right? Now, take it in your hand. Over here, just look that the arrow of the current was over here, which means that the direction of the current was from downwards this pen towards the cap of this pen, right? Now hold it in your right hand such that your thumb of the right hand indicates the direction of the flow of the current. Then the curling of the other fingers will indicate the direction of the magnetic field being produced, right? So if I hold this one like this, now see, my curling of other fingers will be over here. It will try to penetrate this whiteboard, to go inside the paper, to go away from the reader, right? So going away from the reader, we actually denote it by this symbol, which means that this symbol means that it is actually, the B is penetrating. It is going away from the reader. And likewise, if we see that over here it is penetrating, and again it is coming like this, because see, my thumb is in this direction and it will come out from this point. So this point, it will come out. Okay. Now, in the entire section of current and magnetism, this thing, this dot, it indicates that the magnetic field, direction of the magnetic field is coming towards the reader, right? And this notation or indication will mean that this magnetic field is going away from the reader, right? So over here now we can understand that at point A, the value or the magnitude of the magnetic field that is produced, if a compass is being kept over here, the B produced will be mu naught divided by 4 pi multiplied by I d L sine theta divided by R square, right? Now, and like this direction is crossed, so we can say that over here this B, the direction of this B is actually going away from the reader, because when you are reading, you are over here, and if the magnetic line of force it comes like this, it means it is coming towards you, but if it is going away, it means that it is penetrating the paper, right? Now we are going to find out the vectorial representation of the Biot-Savart Law. The vectorial representation of the Biot-Savart Law, if we are going to find out that this is the magnitude, See, for example, over here it is given B, the magnitude, is equals to mu naught divided by 4 pi multiplied by I dl sine theta divided by r square. Right? Now, if we could go back to the concepts of vector, we know that if something is written, say for example, I dl sine theta, which means that this is the cross product, because for dot product we know that cos theta was going to come. But if this is sine theta, it means that simply there is a cross product. So there will be cross product, I cross product of dl? No, absolutely not. Why? Because see, the theta which is being given over here, that is being kept only between r and dl. This is not between I and dl. This is between dl and r, right? And as we know by the convention that theta is being taken positive on the anti-clockwise direction, right? So now what we can do is that we can multiply and divide both the numerator like this. We can multiply the numerator and multiply the denominator by r. So it is going to come out mu naught divided by 4 pi multiplied by I multiplied by this r multiplied by this sine theta multiplied this dl divided by r cube. Now look that over here, let us do like this is dl over here and I on this direction. Right? Now observe that we can write it dl cross product of this r. Right? The direction of dl was in this direction. In this direction, right? The direction of the dl was in this direction and the direction of r was in this direction. Because this is the point of origin. Okay? So now we can write it as mu naught divided by 4 pi multiplied by dl vector cross product of r vector multiplied by r divided by r cube. Right? And we know from the vectors that this vector A will be equal to, say for example, the magnitude of this is the magnitude of this A vector multiplied by the unit vector along A, right? The vector A is actually represented as the magnitude of the vector A multiplied by the unit vector of A. So likewise, if it is R, we can represent it. So we can write it as equals to mu naught divided by 4 pi multiplied by dl cross this unit vector of r multiplied by r, because we can write this vector r as likewise multiplied by I divided by r cube. Now we can cancel this r and r cube as such that r square remains in the denominator side. So the vectorial representation, the ultimate vectorial representation will be mu naught I divided by 4 pi multiplied by the cross product of the dl vector and the unit vector along the r. Right? So from this lecture now we are able to understand that why Oersted actually saw the deflection of this magnetic needle when it was kept near a current carrying conductor, and what would be the magnitude of a magnetic field when it is separated by a distance of r and this DL and R is making an angle of theta, so its magnitude will be equals to mu naught divided by 4 pi multiplied by I DL sin theta divided by R square, because in the Biot-Savart law it is told that it is directly proportional to I, DL and sin theta, and is inversely proportional to R square, where mu naught divided by 4 pi is a constant and mu naught is the permeability of free space, right? And also we have seen about the vectorial representation of the Biot-Savart law, and as we know that this is a cross product, which means that this GL and this R is lying on the same plane, then the direction will be along the axis which is mutually perpendicular to them, right? And alongwise we have found out that what will be the direction of this magnetic field, whether it will be inward the paper or outward the paper. How to determine that? With the help of the Cork-Screw Rule or the right hand thumb rule, where this thumb will indicate the direction of the current and the curling of the other fingers will indicate the direction of the magnetic field. Thank you.